Mud Cushion, a drilling solution. We're Team 26, and I'm Stephen Bright.
And my name is Matthew Wagisback.
I'm Devin Spalagine.
I'm Ethan Roche.
So first off, I'm going to start off by giving an introduction of our team members as well as our advisors and talk about some of their qualifications. So first we have Stephen Bright, a fifth-year petroleum student with knowledge of MPD, as well on some hands-on experience with building small-scale models. Next, we have Ethan Roche, who's a fourth-year petroleum student with knowledge of MPD as well as a one-year internship in the field. So next we have Devin Spalagine, a fifth-year petroleum engineering student with knowledge in MPD as well as 2 years intern experience mapping and analyzing reservoirs. And then we have Matthew Wagisback, which is me, a fifth-year petroleum student with 3 years as a supplemental instructor for PETI 2032, which is our petroleum fluids course here at LSU. So now I'm going to move on to our advisors. We have Dr. Mauricio Almeida, who is a professional and resident at LSU. He is currently employed for Seadrill as a drilling project manager. He spent 9 years as a senior drilling engineer consultant for Petrobras as well. So he's very knowledgeable in the subject. Next we have Daniel Braga, who is a current petroleum graduate student at LSU. He got his undergrad in mechanical engineering and is currently working for Seadrill as a student trainee. So next we have our experimental problem. Our original problem, we were gonna look at the pressures in the riser as you were taking a kick in offshore drilling operations using MPD. So this is actually a big problem in the industry because due to the technology's underuse, not many people know much about what's going on when that pressure or when that kick hits the riser and those pressure fluctuations come in. So originally we decided that we were going to try to study this some way, but then we decided further through our experimental problem that we decided as a group, in order to fully test these pressures adequately, it would cost a lot more than we would be able to acquire budget-wise. So we decided we'd make a smaller adaptation and build a model, a hands-on model that was more cost-efficient procedure for managed pressure drilling using 2 pumps as well as density changes in our fluid. Since many rigs are already equipped with multiple pumps as well as agents to increase or decrease density, we believe this was an easy fix for continuing to drill while taking a kick. And we will do that through multiple diverter lines and test out this new method of diverting the kick safely while still drilling ahead.
So, how are we solving the problem? Well, last semester we began by researching managed pressure drilling and building a foundation of how it operates and why it works. Within doing so, we recognize that when implementing MPD, you can drill ahead while we're taking a kick. This is possible because the choke manifold on the rig floor provides a back pressure and provides an overbalance. So then we worked with our advisor, Daniel Braga, who already had an experiment in mind, and we adapted his take on the cheaper alternative and based a model off of his mock-up. From there, we grabbed a paper from onepetro.org regarding managed pressure drilling in the Gulf of Mexico. It had real-life data, so we could actually scale down our model and compare it to field result. We used Fox's Introduction to Fluid Mechanics, the 8th edition, to scale down the data you see here. So everything from prototype was grabbed from the paper. We then started with the riser ratio, and then we properly scaled down the drill pipe. Then we went to Buckingham Pi theorem, given this data and the new drill pipe and riser, and found a new velocity. We then took that velocity and calculated a flow rate that we would need for our experiment and came up with 30 gallons per minute. which led us to building the model. So now that we knew what the flow rate we needed and the pipe diameters, we were able to compile a list of everything we needed. We rationalized the budget as a team on the imperative parts, both the modest build quality and cheaper. Once the budget was approved by our $49.99 professor, we placed the order with Janet Dugas, and that took several weeks to come in. So during that time, we were able to talk with Wesley Williams and find a safe spot at PERT Lab and find the required PPE to wear while working out there. And then over the past couple weeks, we've actually been able to spend several hours building the model. Turns out we had a couple small parts we needed to go and buy, so we ran to Home Depot and grabbed those. And we can say that the model's 90% done now, and testing should begin shortly. Now, the objectives of the model. So the first obtainable goal is to replicate fluid flow in an offshore riser with a gas kick traveling up the annulus. From there, the two diverter lines we have, we can open them up and actually introduce the closed loop for the mud cushion and the diverter line for the mud with a kick, which is basically the primary function of the model. We'd like to test the plausibility of drilling ahead while diverting the gas kick in the riser with the mud cushion pumped into the upper region of the annulus. From here, you can see we have a primary mud tank, followed by a secondary mud tank. This one will be the one providing the mud cushion, and this will be the normal drilling fluid. From line 1, we'll travel up to the drill pipe, down to the bottom of the riser, where you have a gas injection port, where we can control the amount of gas going in, which will simulate the size of the kick. From there, it'll travel up, head out from line 2, back to the original tank. And then line 3 is going to come up and pump in the heavier mud, and come out line 4, and head back to this tank. You might have some mixing going on in here. We're not quite sure yet. We'll have to play with density and viscosity. Maybe we can limit how much that is, changing the surface tension between the two muds. It's all part of the experiment. Unfortunately, we haven't been able to run any tests, so it's too early to give any results. But we're very optimistic with the setup and design we have, and we're excited to share our results in the next coming weeks. Thanks.
Like Ethan said, our model's 90% done. This means we don't have any actual experimental results yet or physical data to compare to anything with a simulation or real data on paper or anything like that. What we do have is a model of fluid flow in pipes where a fluid of lower density come up the annulus and meet the higher density fluid and inject on top of that. This should create like a barrier between the two where the lighter fluid will not be able to go up through the heavier fluid and create any issues in the riser or in surface equipment up there. So at this contact point, we put a diverter line right below it to where the less dense fluid can exit with the gas kick in it and be handled safely by other equipment and not cause any more issues. And then above that contact point, we put the diverter line for the heavier density fluid where we can create that closed loop system and recirculate that back through however long we need to do that. As far as the application goes, this technology would be used offshore where gas in the riser becomes an issue or just wants to be mitigated basically. It's an alternative to managed pressure drilling. It doesn't do all the bells and whistles that managed pressure drilling has, but it does effectively remove gas from the riser and also allow you to drill ahead at the same time. It doesn't have all the same parts, which means it's also much cheaper than managed pressure drilling. So maybe whereas a larger company can afford to buy all the managed pressure drilling equipment, smaller ones may opt for this option. It's much cheaper and basically accomplishes the same big goal.
So in conclusion, through our research and aid from our experience and knowledgeable resources, our group is extremely confident that our scale model will prove successful of managed pressure drilling. We followed our plans and budget every step of the way to make sure that we finish our project in time. We scaled down a real size model in the PERT lab, which is really convenient, so we can show a first-hand idea of how our method works. And since our great teamwork was so successful, we minimized any problem we had to complete the project the best way possible. Our model is about 90% complete and plan on having it finished within this week or next week, so we can run tests and actually have results to prove that our experiment was a success. Thank you.